Thanks very much for the kind introduction. Thanks for welcoming me here. I tend to say yes to everything that people ask me to do, and I get into trouble. So I'm department chair. That's what school director is, and it's tons of fun, really exciting, and I'm sure that being program chair for CVPR in 2020 is also going to be kind of fun and exciting. And with the growth rate and the number of papers that are being submitted, I'm kind of scared. But yeah, it's going to be an enjoyable ride. So anyway, so I'm going to tell you about some of the work that my group has been doing on sort of deep structured models for group activity recognition, human activity recognition, and related problems. Okay, so please feel free to interrupt me at any times if you have questions. Just to check on the time, how long am I supposed to ramble on for? Okay, but don't, I mean, especially if you chose seats at the front and you need to leave and go somewhere, I won't be offended if you have to take off. Okay, so. I'm interested in human activity recognition as one of the problems that I work on in my work. So what we'd like to do is take in a scene such as this one and answer a bunch of questions about what's happening in this scene. So what are the sort of the sub-problems that when I say activity recognition, what do we want to be able to do? So perhaps first and foremost is we'd like to be able to put bounding boxes around all of the people in a scene like this. And this problem of detection, human detection, is almost a solved problem these days. So I would always say almost. There's always this last niggling couple of % of precision or recall that you're missing, and really getting those is not a trivial matter. So I don't mean that it's totally solved, but it's to the degree that we can sort of do some higher level reasoning on top of these output detections that we can get from state-of-the-art algorithms. Okay, so on top of that, what might we want to do? We might want to figure out where these people are. All right, so if I'm trying to figure out what's happening in a scene, it's helpful to know where we are right now. So for example, I'd like to know that they're in an indoor scene, maybe that they're in a long-term care facility, maybe that's the floor, maybe that is a walker. This sort of context of where am I and what's happening is very important for activity recognition. One of my favorite examples of this is what's happening right now in this scene. Okay, so I'm standing here and I'm waving my hands and I'm making a lot of noise. If you take me and you put me out on the street doing this, I hope that you would sort of, maybe get me some help and say you're kind of worried. You probably wouldn't be sitting there with rapt attention saying, wow, that guy must know a lot of things about computer vision and so forth. So the context really, really matters. Knowing that you're in a long-term care facility, seeing that there's a walker there will help you interpret what has happened in this scene. Okay, so I'd like to do what we classically sort of call action recognition, which would be for each of these people in this scene, put a label on these people. Right? So I'd like to say that person is standing, this person is running, that woman has fallen. I'd like to be able to put those labels on the people. But beyond that, I might want to know why. Why are they doing those things? So what we sometimes call a social role. So why is that person running? Well, she's running to go get help. Why is that person squatting? Well, she's squatting down to comfort the person who has fallen. Right? So there are many different labels that you could put on these people. And they range from sort of the actions they're doing, the objects that are involved, and why are they doing them. Maybe I also want to recognize at a whole scene level the group activity that's happening here. There is a fallen person, and these people around are trying to help that fallen person. Okay, so there are many of these labels that you could put on this scene. And the upshot of this is that they're related. Okay, so understanding what's happening in this scene should involve reasoning over all of these entities together. I need to know where they are, what the objects are, what the individuals are doing to figure out what the group is up to. Okay, and so I think that it's important to sort of model structures and interrelations between entities in a scene. And that's what I'm going to talk about today. Okay, so I'm going to split this talk into three pieces, each of which is sort of based on a few papers that my group has worked on in the past couple of years. So the first thing I'm going to talk about is on what we call label structure. So label structure is going to be about what are the different labels or tags that I can put on a scene, and how are those related, and how can I do joint inference over those to figure out what label should go on one scene. Okay. The second batch of work is going to be on temporal structure, and I'm going to highlight some work that we've done that is about learning to efficiently watch videos in time so that I can label them without having to examine every single frame. And then the final bit of work, I'll talk a bit about group structure. How do we model interactions between people in a scene? Okay, so on to the first part, I'll talk about label structure. And again, please feel free to interrupt me if you have any questions about what's going on here. Okay, so I'll motivate this example by, let's say I have an input image such as this one here, and I have a large set of potential labels that I could put on this scene. Okay, so over here on the right-hand side, these are some of the potential labels. So I could say this is an indoor scene, yes or no. I could say this is an outdoor man-made scene, yes or no. This is a sports field, yes or no. There are cabins or houses, yes or no. There's a baseball, yes or no. Okay, so for each of those labels, it's sort of a binary thing. Is that thing present or not? Okay, so if you pick one of these labels out of here, say batter's box, okay, and you ask, where is the visual evidence in this scene for there being a batter's box? What would you say? Okay, so where is the visual evidence for batter's box in this image? The batter. So you're researchers in there, so you know that we're not going to be talking about this smear of white pixels that's down there. That's not sort of the evidence that there's a batter's box. It's part of it. Okay, it's probably the weaker part of there being a batter's box here. It's that you see this is a baseball diamond, you see there's a batter, you see that he's swinging. There's probably a batter's box there. If you go in and look, yeah, there's some pixels that are sort of white chalk that are probably part of the batter's box. So it doesn't really make sense to sort of build algorithms that are going to do batter's box detection from this scene by just looking at those white pixels. Okay, it's sort of a holistic thing. I look at the whole scene to figure out what's going on. Okay, so basically there are relationships between these labels. So I've sort of highlighted some of them here that are sort of either positive correlations or negative correlations. So some elements tend to appear together, some of them tend to appear in different scenes. Right? And so it's sort of unlikely that you would see a sports field and a trench together in the same scene. Right? Maybe not impossible. There are different types of relationships that you could have, but there are sort of positive and negative reinforcements. So what I'm going to do is build a model that can leverage this type of information and learn how to tag an image with all these concepts utilizing either hierarchical structure or label structure or relationships between labels. Okay, so this is how this is going to go. So your normal sort of approach to tagging an image with some concept would be the following. Take in an input image, build some sort of visual architecture, some sort of convolutional neural network that could output, let's say a vector. Let's say we've got a bunch of independent logistics which say, is there a batter's box, yes or no? Is there a sports field, yes or no? Is there a batter, yes or no? Is there a trench, yes or no? Okay, so it's multi-label, so we could have a bunch of logistics that come output from there. Okay, so that's all well and good, but it's very difficult to especially answer those concepts such as batter's box. We have very little visual evidence for them. So what we're going to do is we're going to build on top of that. So I'll call those our initial activations. So each of these, this is corresponding to how much do I think that each of those many concepts is present in the scene based on just a CNN that looks at the image and says, is that thing present or not? Okay, so who remembers probabilistic graphical models? Do you remember those probabilistic graphical models? Okay, so probabilistic graphical models, good stuff, okay? One way of viewing what we're doing now is we're going to do some sort of inference on top of these as random variables. It's going to be very much akin to a message passing type of procedure in probabilistic graphical models. The difference is that we're going to learn all of the potential functions and have it all fully integrated training, so we can do joint training on both this visual architecture as well as the inference mechanism that goes on top of them. Okay, so we're going to do sort of have an inference machine that's going to operate on top of that graph of labels, which is going to use those initial activations, pass messages around to sort of refine probabilities, refine estimates of which of those concepts are present based upon activations of all of the concepts that were present in a scene. Okay? So this is going to be a fully end-to-end trainable system so that I can backpropagate all the way from my final results through both this inference machine as well as the visual architecture that I have. Okay, so now I'm going to dive in a little bit more deeply on what that thing's going to look like. Okay, I'll skip that for a minute. Okay, so here's what this is going to look like. I'll start out by doing top-down inference. Okay, so again, I have an input image. It goes through a visual architecture, a CNN. That produces probabilities for each of my possible labels that I have that I could put on this scene. Okay, so the first thing I'll do is I'll start with sort of labels that are at the top of this structure. Things such as, is this an indoor or outdoor scene? Is it man-made? Is it natural? through to sort of mid-level concepts, perhaps things such as, is it a sports field or not, down to the lowest level concepts like baseballs and bats and so forth. Okay, so what I'm going to do is take the visual activations from a CNN. Okay, so again, input image, pass it through a CNN. For each concept that I have, at each layer of this, I will have some initial activation, sort of XIT, which is to denote how much do I think that there is a baseball present in this scene based on the original CNN that just looks at the entire image. I'm then going to proceed in a top-down method, doing inference to refine these probabilities. The way that I'm going to form a new refined probability, so this is going to be some concept I and some layer T, starting from the top going down, is I'm going to base that off first other related concepts that are in the same layer of this hierarchy. Okay, so they're going to be probabilities for the other concepts that are in this layer of the hierarchy. I'm going to have a bunch of weights, which are going to specify how much those concepts should reinforce each other or not. Okay, so these things can say things such as, well, if this is an indoor scene, it's very likely that it's a man-made scene. Okay, there can be some weight that says those two things should reinforce each other. Okay, so then what we do is we have something that passes information top-down. So from refined probabilities that we get at a previous layer, we can have, again, weights on those that will pass information downward to the next layer. So again, these can reinforce things such as if there's an outdoor man-made scene, how much does that go together with baseball diamond? Right? And so again, we'll have a bunch of weights V that will control how much those relate to each other. Okay. Okay, and so all of those weights, these H's and these V's, are parameters that we can train in end-to-end fashion. And again, akin to sort of belief propagation, message passing, these are, in a way, these are the parameters of potential functions that would relate together these different concepts. Okay, and so there's no reason why we just have to pass this information top down. We could also do a bottom-up pass to pass information up the graph in the other direction. Okay, and so we can do sort of bidirectional inference over this graph, where we don't just pass information top down, but we can run an inference procedure top down as well as one bottom up. Okay, and so here the notation is basically if I can run these message passings from the top down, I can get refined probabilities here for each node. I can run similarly, I could run a bottom-up procedure where I gather information from the bottom, pass it up, and then I can have additional parameters U that will be used to combine those two together. Right? So I get a bottom-up inference procedure, I get a top-down inference procedure, I can combine those two together, reweight them to figure out what the final estimate should be. So we can do that sort of top-down inference, bottom-up inference, and then combine the two results together and bidirectionally. Okay. So some details, I think people have already sort of cottoned on to this, that there's some details about how do you train this thing. We can also enforce things such as there shall only be a positive correlation between a pair of labels. We could enforce there shall be no correlation in the sense of this inference procedure between labels, or there shall be a negative one. So what you can do is you can basically decompose these connections between nodes, either within a layer or across layer. We can decompose them into sort of positive correlation and negative correlation. We can use ReLUs to enforce that the interaction terms that we're doing must be positive, and then constrain the weights in these two to be positive as well, in order to make sure we get either positive only or negative only correlations if we want to do that. Okay, so there's some technical details around that, and I'll kind of happy to stop and talk more, but it's basically, there's more and more of this. You can decompose things into sort of positive only with a plus sign, negative only with a negative sign, enforcing the weights must be positive, and using ReLUs as activation functions to enforce that you get positive only components to the message passing. Okay, so that's sort of this sort of inference machine that we've developed. And what you do is you take this visual architecture, which can produce estimates of whether things are present in the scene or not. And then on top of that, you can add this structured inference procedure that can then message pass around there. The interesting thing about this is that you can use this not only for just purely visual inference. So from an image, do all this inference. You can also use it if you have side information that's provided for you. Okay, so what this looks like then is so a purely visual approach would be the following. Take an image, pass it through a CNN, get these initial activations, do my message passing up and down to refine those labels, get some refined probabilities on things, okay? Output things like it's an outdoor man-made scene, it's a sports field, batter's box, et cetera, et cetera. But many times you have external metadata as well. So for example, somebody might provide information like GPS coordinates that tell me that this is an outdoor man-made scene. What you can do then is you could fix some of the nodes in your hierarchy, pass them through a logit or a reverse sigmoid to sort of turn that into a bit of a softer probability, fix those nodes, pretend that you got those from visual activation, and then still run my message passing, my information propagation around. And so I think it's kind of nice that you can take this type of architecture and do the sort of probabilistic inference types of things that you often did with graphical models, where you could observe different nodes. And we have some data sets where we've done experiments with this where you know some things about the images. You could know the users who took these images. Maybe you know GPS coordinates. Maybe you know some labels. And then you can refine out the other labels that you don't have good estimates for based on that. All right. OK, so we've done experiments with a few different image data sets on this. So NUS-wide is probably one of the larger of these sort of multi-label image data sets. It's Flickr images, and there are image groups, which are basically metadata about the users who took these photographs. There are a bunch of different concepts, 1,000 different tags you could put on images. There's another older Sun 397 data set, which has labels that are organized into 3 different concept levels. There's sort of 3 course level labels, 16 general ones, and 397 fine-grained labels. And we've done experiments where you can either fully infer all of these labels, or you can fix some of them and infer the rest. So I don't know that I can highlight a couple of these things. I mean, as always in these sort of talks, you can read the paper, there are graphs where we do ablation studies and things get better as you add different parts of this. So the usual sort of baselines, I think people are asking, well, can't you just do this in a CNN? That's sort of a CNN with logistics. So if you just have a CNN, you train it, you have independent logistics for each of the multi-label tags that you have on an image. That's sort of the green bar. These are accuracies in this case. So you sort of show improvement over that. The BINN is the top-down, bottom-up message passing. The structured version is where we add some structure to it. And it depends on the data set. Some of them have a very sort of not much correlation between labels. And in those cases, it doesn't help very much to add this. Times when there is sort of a relationship between labels, our method can learn how to handle that. Qualitatively, you sort of, here are some examples of the types of images that we have. The top row is the ground truth label. And then the second row is what a CNN with independent logistics produces. And then our method produces the one on the bottom. And I think, again, your research in the field, you know that ground truth labeling is often inaccurate. Okay, and it's incomplete. There are things that are missing. So for example, this image has the label railroad. The CNN produces statue, buildings, and person. Our method produces railroad, person, and sky. Person is incorrect. This is not a person image, even though there's a person in it. Right? So these sort of things are quite common, and so the accuracy is good. It produces quite reasonable things and reinforces reasonable interactions between these different tags that are possible. It's unclear. So I think the bigger experiments that we've done, I'm just going to skip ahead a couple of, skip over this. Recently, we tried this out with the YouTube Atm Data Set. So this is I think this is probably the largest multi-label task that I know of. It's 8 million YouTube videos. There are 2 versions of this data set, V1 and V2, but basically there are 8 million videos, about 500,000 hours of video, and 4,800 possible labels. The label set's quite diverse here. It's everything from Lady Gaga video to cat video. Right? So there's huge variety in things, and again, there are a lot of interesting relationships. We built a label graph over top of those, and if you want to know details of how we encode videos, it's basically per frame CNN, and then you just mean pool the features for them. We do not go back and fine-tune these CNNs for feature extraction. It's really prohibitive to do so. Google provides pre-trained inception V4, I think it is, features that are extracted from every single frame. It's really necessary because going back and fine-tuning 500,000 hours of video doesn't really work. So we mean pool the features over all the video frames. that might seem really naive if you've never done video stuff before. It's actually kind of okay. So if you have like cat in toaster videos, you don't really have much temporal signal to them. There'll be a frame where there's the cat with its face through a piece of bread. You see that, you're good. Mean pooling, just fine. You don't really need to LSTM them. We've tried things like that. It doesn't help a lot. Okay, so you basically get a mean pooled feature vector for this video. You can then do this inference procedure. And again, we've sort of shown comparing sort of mean average precisions or geometric mean average precisions. For both of those settings, adding this inference mechanism on top of the features that you get from a simple sort of averaging improves performance by a few percentage points of MAP or GAP. Okay, so let's switch gears a little bit now and talk about temporal structure. The last little segue there was about how in the YouTube Atm data set, we don't have temporal labels. We just have video level labels about what people are doing. Okay, so I'm going to highlight a couple of pieces of work that we've done toward video labeling, where we're actually going to label things in time. Okay, so rather than just having labels at the video level that says this is a Lady Gaga video, I like to say, these frames of this video involve particular actions. So one effort that we did is we took a data set called Thumos, which is a pretty large activity recognition data set, and re-annotated it with a bunch of lower level actions that were actually annotated in time. Okay, so videos such as this one, this is a weightlifting video. It might just be annotated with weightlifting or clean and jerk. We actually went and annotated with these frames have the clean and jerk action. This part is where the person is sitting down. This person is where he's entered a squatting pose. This is where he's picking something up. We've annotated it with sort of much more detailed level of labels in time. Right? So the original Thumos data set, these are statistics on the number of annotations, number of categories, average number of labels per frame, average number of classes per video, et cetera. So the multi-Thumos data set that we created has sort of much more in terms of the amount of labels and the diversity of them in each frame. Okay, so I'm going to switch into sort of some work on, as promised, on watching YouTube videos. Okay, so this task is going to be what's called action detection. So for those who are not familiar with it, we have an input video like this one. We want to find the instance of the running action. Okay, so the way that this problem is formulated is that I want to, over the time sequence, say that there was an instance of the running action that began at this time and ended at that time. There was an instance of the talking action that began at this time and ended at that time. So again, I'm not sure how many people are computer vision people, but there's a sort of difference between detection and classification. There's distances between sort of semantic segmentation and instance segmentation. There's an analogous difference here, that we're not saying running, talking. We're saying there was one running here, there was one talking here. You can definitely quibble with me about what the definitions of these things should be. Do I care how many steps the person took while running? We could do that as well. We could say 1 step, 2 steps, 3 steps, 4 steps, et cetera. But we're detecting these instances. Okay, so what we'd like to do is we'd like to build a model that can detect these instances. Okay, the dominant paradigm in this type of thing is dense processing of videos. Basically what you tend to do is you look at every single frame in the video, and maybe you produce some action proposals, or you do simple sliding window type processing. Okay, so you look at every single frame in the video, you look at them, you say, frame, here are my proposals. Is that a run, yes or no? Is that a jump, yes or no? Is that a talking, yes or no? That's sort of the dominant approach in computer vision. So instead what we said is, well, that seems very naive. Okay, so let's say I'm looking for baseball swings. Okay, my job is build an action detector that's going to find baseball swings in YouTube videos. Let me look at the first frame of a video. Okay, if I see that it's in a bowling alley, okay, maybe I could just stop right there. I say it's very, very unlikely that anybody's going to do a baseball swing in a bowling alley. As per the previous discussion, it's possible. Okay, so exclusivity is always a bit dangerous, but if I'm aiming for some particular mean average precision value and I'm constrained on resources or I don't really want to look at everything, it's probably a bad idea to keep watching that video of a bowling alley to see if somebody's going to pick up a baseball bat and swing it, okay? Could happen, let's just say no. All right, on the other hand, if I look at this video and I say, that looks like a baseball diamond, what should I do next? It's probably not necessary to look at the next frame of that video because it's probably also a far-field view of a baseball diamond. There's not much additional information to be gained from looking at the next frame of that video. Instead, maybe I decide to jump forward and look at the frame that's here. Okay, a bunch of people celebrating at home plate. Looks interesting. Let's back up. Oh, somebody rounding first base, giving a high five. Let's back up a little bit more. Oh, pitcher's about to throw, jump forward. Okay, baseball swing, done. That's the type of processing paradigm that I'm going to be working under in this work. Okay, so we're going to not sequentially process all the frames in the video. We're going to look at a frame of video, see what's in it. Based on that, I can decide whether I should continue looking at this video, where should I jump in this video, should I determine that I have output a baseball swing or not. Okay, so that's the model that we're going to look at. Okay, let me illustrate how this model works. Down at the bottom, this is the input video. Up at the top, this is going to be sort of my canvas for writing outputs that my model is going to produce. Okay, so the model chooses a frame in the video. Maybe I start with the first frame of the video. Maybe I start somewhere in the middle. I choose a frame. I put it through a CNN that's going to give me some representation for that content of that frame. I'm going to put that into a recurrent neural network that's going to store what have I seen so far. Okay, so I look at this frame, put it through that RNN. It's going to say, well, here's what I've seen up to now. That RNN is going to output a few things. Right? It's going to output an instance hypothesis or a detection instance for some action. Okay, so for example, it's going to say, I believe, based on this, there's going to be a baseball swing. And that can have an offset. So the other nice thing about this is that this model, it can see the beginning of a baseball swing and say there is one from now into the future, or it could see the end of a baseball swing and say there is one from now to the past. Okay, so it gets to output an instance of this sort of detection. The other thing that it needs to be able to do is it needs to be able to say, I don't like the thing that I just output. I'm not ready to output a detection instance yet. Okay, so it's always going to output something. This is sort of, it's very convenient to let it always output something. Then it can also have a sort of a binary indicator variable that's going to say that one didn't count. All right, because sometimes it's not going to be confident enough yet to actually output that thing. Okay. The next thing that it needs to do is it needs to output where should I look next. Okay. So these are going to be expressed. This thing, the detection instance, is relative to where I am now. Same thing here. Where should I jump next? Okay. I jump to that place. I read the frame that's there. I encode it with a CNN. And I, again, pass it into that recurrent neural network. Right? So again, now this RNN has stored. I've seen this frame. I output something. I jumped over here. I saw this thing. It's maintaining that state. Again, it's going to output a detection instance hypothesis saying maybe there's a baseball swing here, offset some amount from the current time. And again, it can say, I don't trust this. Jump back a few frames, examine that, output a detection. Maybe this time I do trust it. Write it up to the detection canvas up here and say that's a detection output, and continue. Okay, so this is the model that we developed for learning how to watch YouTube videos to detect actions. So as you can see here, there are a couple of things that are sort of okay, and a couple of things that are not easily differentiable. Okay, so you've got the next frame to glimpse. That's something that's not going to be differentiable. So I'm going to need to use reinforcement learning to train that. And I've also got this indicator variable, do I trust the detection that I just output, yes or no? That's also something that's going to be a hard decision that I need to train with reinforcement learning. there are a couple of parts that you need to train. You basically need to train classification loss for the detection instances that you produce. Right? And so we have basically, you want sort of cross-entropy classification loss, so you get the class label correct when you output things. You also have a localization loss as well. So in action localization, you want to make sure that the detection that you output is close enough to the thing that you're outputting. Usually what people do is they do an intersection over union criterion when it comes to test time to measure how many things you got correct or not, but that's not easy to train with. So instead, you usually do something that's simpler to train with. You basically do an L2 distance localization loss. That's something you can train with quite easily. So all of this is fine. Okay, so you can backpropagate through these. These are differentiable. It's all okay. And then what you do is you basically do sampling using reinforce to basically sample a bunch of sequences, gather up rewards for those, take derivatives of them, and so forth to deal with the non-differentiable components. There's some other fun stories about this work. So, okay, it's being recorded. I'm totally fine with saying this. But so the measure that we're using for success is average precision across all the categories, so mean average precision. So I'm not sure how many, do you know the criterion average precision? Do you know that term? Okay, so average precision. Do you know how to write code to implement average precision? Okay, so how do you do average precision calculations? Okay, usually what you do is you get a bunch of scores. Okay, so you've got a bunch of detections. Okay, and those have scores. Okay, so high scores to low scores. Okay. Each of those detections is either a correct detection or an incorrect detection. Okay, so usually you sort the scores in descending order, then you start counting, and if you see a true positive, you increment recall and you change precision. If you see a negative, you don't increment recall and you decrement precision. Okay, this is kind of what you do. Okay, what if the scores are tied? What if you have a few examples where they have the same score by the detector? What should you do? It's not really a trick question, but it's a corner case that really matters. So a good idea is to randomly order the things that have the same score. Okay, if there are any detection outputs that have the same score, you should randomly add some noise to all of them so there are no ties, and you just randomly break them. What the people who did Pascal and Thumos and these other challenges did was that they put all of the ground truth positives first. Okay, seems fine because why would there ever be tied scores? Well, reinforcement learning is pretty smart, is why there might be tied scores. Because reinforcement learning doesn't really know what's going on, but hey, I get a good score if I just give everything the same score. It seems like everything's working, everything's fine. So what it did was, it wasn't able to find that solution, but it would not move out of that solution. And that's actually a really good strategy. If the video is really hard, just give everything the same score, and all of a sudden, you get a pretty good result. It's not bad. Don't move from that. And so reinforcement learning is pretty smart. And so the first version of this work that we did it wasn't our code for doing average precision calculation. It was someone else's code everybody had been using for a long time. Has this kind of bug in it, I guess. And reinforcement learning sort of found it. We redid it, and the results dropped a bit. They were still better than baselines. It was all still OK, but it used to be a lot better. Yeah. To me, what's interesting is we can basically get results that are better than at that time the state of the art, and we only glimpse 2% of the frames in a video. Right? So we set that number. We're only going to look at 2% of the frames. Here's the result we can get. I think this is really exciting because it lets you potentially develop methods that can decide where to look in a scene, active vision. We did some follow-up work at CVPR 2017, I guess it was this year, last year, on using this to sort of learn how to learn action categories you've never seen before. So I really feel that there's a lot of potential to build these types of techniques for interesting other problems. So here's some fun learned policies. I will show them as videos, but basically here's one as just a still frame of sort of where it's looking. Okay, so here is time. The top row, this is the ground truth. This is a javelin throw. So the ground truth annotation for the javelin throw happened here. This is the prediction that our model produced. It produced that by starting here, then it jumped forward, jumped forward, jumped forward, jumped forward, checked back a little bit, output, jump forward, jump forward. So this was the path that it took through this video. Okay, so this sort of long jumps forward probably makes sense, right? That's a very common thing. I saw that. I want to really jump forward ahead. It tends not to do much of this sort of niggling around individual frames. It's sort of unnecessary. So here's that one in sort of video time. These are the frames that it looks at. This one, go back just to make sure. Looks good. Now back. And you can see, because that one frame, it's kind of ambiguous, just as one frame. Getting one more frame of context around it probably helps you be confident, yes, that was a javelin throw there. And yeah, you need all that. Good. And so the red box, that was when it thought it was happening. Here's another one. It's a hammer throw. So there's some unknown amount of time where the person's going to sort of get ready, spin a few times, and then go. But once you sort of see one of these frames, you can kind of know, OK, there's going to be a javelin, there's going to be a hammer throw. It's going to take this amount of time. I'm good. This one's a long jump. And so you notice it doesn't say long jump till at the end. It sort of says, OK, now person's fully committed. OK, he's going down there. I'm happy. Right? So it's basically about here where it said long jump going to happen. And so just to play that one again, so when you see the context of it, all right? It's sort of that. Yeah. All right. So it's sort of not detecting long jump until this very late frame. Not yet. Here, that's when it said long jump, right? Once it sees the person that far down the path, it's gone, right? So it didn't say long jump at this point. It didn't know yet. It wasn't until it was very, very far down the path. So to be honest, the thing that I'm most excited about with this type of work is active vision problems, such as in robot vision. So robot vision, I'm starting collaboration with some roboticist who does UAVs, and consider the problem of, given a UAV, go find all of the people in this area, a wide area. You can't see the whole area from one view. You've got to plan, where should I go next? Okay, and I think that it's, when all the information is present in this video, you can do all sorts of things where you sort of scale space analyses, and all these are great. But I feel that this lets you try this sort of, I see this information, where should I go next? To me, that's really the crucial thing. So I think this is complementary to the scale space things. Likely the performance gains would be smaller once you add those techniques. Cool, so I mentioned someone was asking about sort of ablation studies and comparisons. So we did things such as, if you take away the binary variable that lets you predict or not predict, performance drops a lot. So if you force the model to always output a detection, even if it lets it have a score, it's not very good. The location output, so allowing it to sort of shift in time is very important. We do sort of uniform sampling as a baseline. So rather than choosing where to look, you just uniform sample a bunch of frames. Again, it doesn't work as well as our model. Okay, so there's a bunch of different things like that. Okay. So then the last part of this talk that I wanted to go over was some of our work on analyzing group structure interactions between multiple people. So again, we've got a series of papers on that. I'll just talk about one that's a sort of recent bit on that. As a researcher in Canada, I know if you're an academic, you know about this sort of when you write grant proposals, you have to justify that they're of benefit to Canada. It's important that you do work that's good for Canada. So this work is good for Canada. It solves a very important problem for Canadians, and that is who has the puck. Okay. So I like this image because sort of you ask who has the puck, and I promise there's 0 puck pixels in this image. There really are, but who has it? Do you know? This guy, right? Maybe if you've never watched hockey a lot, you still might know.
I feel like this is actually more benefit to Americans who apparently.
Exactly. Yeah, the glowing. We need the glowing thing. Exactly. Well, that's true. It's okay. So it's sort of a reasoning thing that we do. And just, we've been doing problems like this for a while. This is sort of pre-deep learning 2011 work, probably 2012 that we did. This field hockey. The person with the pink box around it, that's the person who we think has the ball right now. This is based on hog features and basically analyzing the poses of the people and figuring out who it is. And you can tell, basically, if everybody's looking in this direction, facing there, it's probably that person. And we make some mistakes. We confuse the person with the referee, but it's generally pointing in the right direction. So fast forwarding a bit to 2017, and these are the sorts of things we're looking at now. These are trajectories from an NBA game. So in the NBA, we have cameras that track all of the players and the ball, give you back coordinates on the floor of where everybody is. From trajectories such as these, we're answering questions, which team is this? So the blue team, which of the NBA teams was that? Maybe you could ask, who was this particular player X? You could also ask predictive questions, like will this shot be successful? Where is the next pass going to take place? So we've developed methods for doing all of these things. I'll talk about an earlier one that we did on deep learning stuff. We do this on hockey videos as well. So I'm mentioning that I work closely with a company in Montreal called Sportlogique. They are amazing. They provide data to essentially all the NHL teams that, basically where are all of the players on the ice, who are they, what actions have they performed. Essentially every time somebody touches the puck, they know what happened. And a lot of that stuff is computer vision that's making that happen. So basically you get in broadcast videos like this. You can do homography estimation to figure out mappings from this to rink coordinates so that I can know that if I detect a player at this location here and assume that the bottom of this bounding box is his feet, I can put him on the rink right there. And this is all automatic. Computer vision works these days. It's amazing. So basically, from that, you basically then can get trajectories of players, and you can get their IDs as well. Basically, if you can read their jersey numbers one time, you're good. And so you can basically figure out who these players are. You get these trajectories. And now, if you'd like to know what they're doing, basically from that, you'd like to say, well, I'd like to know that player 1 here is trying to pass the puck to player 5, and maybe player 2 is trying to stop that from happening. I'd like to know something about that based on these trajectories. Okay, so skip that. Okay, so what we will do is we'll sort of build essentially trajectory analysis methods. One of the challenges in multi-person activity is that you need to kind of ground your representation based on something to do with which player is which. Okay, so it's very hard to see the puck. It really is a hard thing to know that from the pixels themselves. So what we do is we have a key player which we assume has the puck. And either we infer that automatically or we assume that we have that from some metadata. Okay, so sometimes you can know who has the puck. They sometimes put sensors in the puck, et cetera, et cetera. But we could also infer that by doing some pooling strategy or different players. Okay, but we're going to have this key player who's going to be the one who has the puck. And then we'll build networks that represent everybody on the ice relative to that person who is the key player. Okay, so we've got a couple of different approaches for modeling this, one of which we call our share compare trajectory network and one we call our stacked trajectory network, whether we're basically comparing players or whether we're just stacking all their feature representations together. So I'll just talk a little bit about this share compare network structure. So what it is basically it takes as input the trajectories of all of the players, and those are going to be represented in a essentially world coordinate system, which is the rink coordinates. Okay, so I've mapped already from the input video to this rink coordinate system based on homographies, player detections, and tracking. So I have these trajectories. And now my job is to build a network that can, for example, classify this as this play right here, this was a pass, this was a dump out, this was a dump in, this was a shot. Okay. So here's what that network is going to look like. It's going to basically be a convnet that operates over top of trajectories. Okay, so I will have a shared trajectory network that I'm going to reuse on each of these players. So these are going to be shared parameters that are going to run over each of the individual players that's in this scene. They're going to be the usual sort of thing. I can do convolution in 1D over these player trajectories. It's two 1D signals, x coordinate and y coordinate, and I can run a convolution over those. I can do pooling operators on top of that. Those are used to then get feature vectors for describing each of the individual players. I can then stack those together, and then I could do comparisons between those players. So for example, I can compare the key player to this player 2, compare the key player to this player 3, compare the key player to this player 4, and again have conv and pooling parameters that do that comparison. Right? And so there are different ways which you could structure this, and we've experimented with a few. In this setup, we have shared parameters that are going to go over top of each of those trajectories. Then we're going to have shared comparison parameters that are going to compare every person to the key player, basically measuring relative coordinates and relative positions to that person. You can do other variants as well. You can concatenate all of those together and then do some sort of classification or prediction if that's what you wish. Okay, so that first layer, what it's going to do is it's going to take in trajectories that are of the form x-coordinate, y-coordinate. Here I'm talking about one trajectory over time. Right? So this is 5 time steps of that one trajectory. And what you'd like to do is you'd like to learn filters that are going to correspond to, for example, a continuous motion in one direction, taking a sort of a side step to another direction, maybe turning the other way. You're going to learn filters that correspond to that. Okay, so we'll do that by having some sort of kernel that's going to have a size c by k by m. It's going to run over top of this input signal, filter or convolve it across this time signal, get a second filter, do the same thing, et cetera, et cetera. And then I'll do that at a second level. So there can be invariances to this. There's definitely a temporal invariance because I'm going to be taking the same filter and then running it over time and then pooling. It can be a relative measure, but it can also have absolute coordinates in it, right? So it can know, we're not constraining these weights in any particular way, right? So it could actually know I'm in the top left-hand corner of the rink. Right? It can know absolute position if it cares to learn that. Okay, so then we stack those things together. We again have similar sort of parameters that we learn, conv and pooling over top of combinations of people as well. Okay, so we've done a couple of different things. We did event recognition on Sport Logic, provided us with data from NHL hockey games. We do event recognition on there. We have NBA trajectories as well. We use those to do team identification. Okay, so event recognition. We used 6 different event classes, so pass, dump in, dump out, shot, line carry, carrying a puck across the line, puck protection events, and we're using a sort of share compare network to predict the event labels. Okay, so what the data set looks like, this was an older version of their tracking system. It's even better now. The trajectories were not perfect in that case. I mean, what happens often, the camera, it's a broadcast camera, it's moving around. The people go out of the field of view and come back in. And so nowadays they've got even better models for tracking them to get linked together trajectories, but they're pretty good. Right? They're pretty good trajectories of what the people are doing. Here's a sort of a distribution, sort of imbalanced real data sets. It's not sort of nicely balanced. Passes are by far the most common of these events that we were looking at. Things like puck protection, dump-ins are much fewer. So we're using relatively short trajectories in this case. They're only 16 frames long. So it's a really short amount of time that you're using to estimate what's happening. Hockey's a pretty fast-paced game. There's not a lot of sort of these, complicated plays, perhaps, that really need temporal structure. Okay, so in this method, for training, we have the ground truth annotation for who has the puck. In testing, we either infer that by doing a max pooling type approach, or we can actually assume that we know that who that key player is. Here are some of the average precisions and mean APs of the different sorts of trajectories that we're using. These are either with the unknown key player or with the known key players. Those are the different events. We compare this to a bunch of different baselines. So improved dense trajectories is sort of a non-deep learning, handcrafted trajectory representation. People who are familiar with improved dense trajectories, they're both visual features as well as a trajectory one. We're using the trajectory component. We also used comparisons to visual features. So our method doesn't strictly use the visual features. It's only using the trajectories of the players. So it kind of throws away the pixels once it knows the trajectories. We also compared to sort of C3D features that are actually looking at the pixels of the person, and it's complementary and better in terms of accuracies. So, okay, so that was events on Sport Logic data set. We also tried things for team classification on the NBA data set. Just to remind you, the type of task we were doing was, given a possession like this, which NBA team was that? So I was pretty impressed. The upshot of all of this is, so there are 30 NBA teams, right? So chance performance is about 3%, right? I saw that possession, 3% chance of figuring out who it is. The network that we learned can do 25% accuracy on a single possession. So just one NBA possession, bring the ball down the court, take a shot, 25% accuracy. If you do some very simple majority voting over all the possessions in a game, we can get 95% accuracy over the whole game. So this network can somehow learn these patterns of what different teams tend to do, and it can figure out which team this is. So again, we've used similar things to do prediction, right? So interesting things are, will this shot be successful, yes or no? Will the next thing be a pass or dribbling? Those sort of predictions are possible as well. The entropy is quite high for those. I mean, the games are interesting. It's not predictable what the team's going to do, but our thing can do better than chance performance at predicting what's going to happen next. So I just want to say thanks to my team. So these are my students. I have about 20 grad students and postdocs, and they do all this hard work, and I get to stand up and talk about it. But really, they're awesome, and I really appreciate their hard work, so I can come and talk with you about this stuff. So thanks very much for listening. I appreciate your time.